Hi. So I thought I'd do a video on the I2C Bus since there's so many little sensors that you can get, like accelerometers or compasses or gyroscopes, etc., that are available that use the I2C Bus. And I like it a lot because it just uses two I/O pins on the microcontroller. I2C stands for IIC, or it's also called an I2C bus. IIC stands for Integrated Circuit Communications, I believe. I'm not sure if the C stands for circuit or communications. It's a copyrighted name, but some people call it the TWI bus, or two-wire interface bus. The ATMEGA calls it that, but it's the same thing. It was developed by Philips Semiconductor, who's now NXP, in the early 1980s, and it allows you to connect up multiple slaves and also multiple masters on the same pair of wires. So for every new slave you add, you don't have to add any more wires, like the SPI bus, for example. A master is defined as a device that actually clocks the data. It controls the clock pin. I forgot to mention the two pins are clock and data, SCL and SDA. The clock pin simply synchronizes the data so that the devices can read it, and the master is the one that drives it. The slaves can affect the clock. They can do something called clock stretching and slow down the clock if they can't keep up with the data rate, but most devices that you'll see today probably can't do that or don't need to do that because they're fast enough. Because they're paralleled up like this, the drivers for each of the pins on each of the devices here are open drain or open collector, which means that the devices can only pull the wires down to ground. They can't pull them high, and that's why we've got two pull-up resistors here, one on each of the wires. The pull-ups pull the wire or the signal line up to the VCC voltage, whatever that is, when these devices aren't driving it. You still get a clock wave out of it, but it just allows you to parallel up many devices without any contentions. How you differentiate one slave from the other? Well, each slave has a unique 7-bit address, and you won't have more than one accelerometer most likely on the bus, but an accelerometer from a single manufacturer, the common one that I've seen lots of is the ADXL345 from Analog Devices, and it has a unique 7-bit address, but it'll be different from that of a different manufacturer's accelerometer or a pressure sensor or a gyroscope or a magnetometer or whatever. And that's how you differentiate them. The master has to send out that 7-bit address, and that signals to the slave that has that address that it's being talked to, and the master can communicate that way. And the slaves that don't have that address are just going to ignore what's going on. You can also have multiple masters, more than one master on the bus. And when I describe the signals here, I'll explain how the masters can communicate with each other to tell each other that the bus is busy and not to use it. So the normal state here, when nobody is active, is the data lines are held high, or the clock and the data lines are held high by the pull-up resistors, and the data is clocked in with the clock line here, and it's clocked in when the clock is low. That is, the data is not allowed to change when the clock line is low. It can only change when the clock line is high. Sorry, I got that wrong. Written right in front of me and I mixed it up. The data is allowed to change when the clock is low, but is not allowed to change when the clock is high. And that leads to two different conditions that synchronize communications on the data bus. So when a master wants to take control of the data bus, it issues what's called a start condition here, where it pulls the clock or the data line low while the clock line is still high. And that signals to the bus that I'm going to take the bus and everybody else is to stay off of it. All the other masters are to stay off of it. It also tells the slaves to wake up and get ready. And then when the master has finished communicating on the bus, it will send what's called a start condition. And what that happens, or what it does there, is it holds, did I call it a start condition? It sends a stop condition. Getting confused here. So when it's finished communication, the stop condition is issued, which it allows the clock line to go high while it holds the data line low. Again, it violates that data not allowed condition here. But that signals to the bus that I've finished using the bus. Anybody else who wants to use it can now use it. Now, let's look at what actually happens here. So I'm going to talk about a sequential read here. What the master does when it wants to talk to somebody on the bus, it first of all issues the start condition, and then it clocks out the 7 bits for the address of the slave it wants to talk to. The 8th bit here is called the read-write bit, and it tells the slave what it wants to do with the slave. Is it going to write to the slave, or is it going to read from the slave? It then clocks out one more clock, and the slave that has that address, it acknowledges by pulling the data line low in this clock cycle here, and that just tells the master that somebody is out there and is ready to communicate. So in a sequential read here, the master clocks out the 7-bit address, followed by the read bit, read-write bit being high, indicates to the slave that it wants to read from it. The slave acknowledges, and then the master starts issuing clock pulses for as long as it wants to read bytes of data. And by the way, the data communication on the bus is byte at a time, 8 bits at a time. So what the slave does is it'll put out its data 8 bits at a time with each clock, and then the master will issue one more clock, and then since the master is receiving the data, it will acknowledge by pulling the acknowledge line low. And this will continue. The master can keep clocking for as long as it needs to get the data that it wants. Now, inside each slave device, there's a register pointer, or we can call it an address pointer, that gets set, and I'll show you how to set that in a moment. And so whenever a data byte is read from the device, from the slave, it will read from the address pointed to by that pointer, and then that pointer increments to the next address, and the next read will just read from the next address. So this will continue on until the master issues a not acknowledge by allowing the bus to go high on the 9th clock, and then it issues a stop condition to tell the bus and everybody else on it that it's finished. Now typically when you're communicating on the bus, you're not going to do this kind of a communication because you don't know where that address pointer actually is. Once it's set, it stays there. It doesn't get lost unless the power is turned off or something like that. But now what I'll show you here is a write to the bus, and I'm going to write a single byte of data to a single register in the device. So the master issues a start, then the slave bit, or the slave address, the 7-bit address, and this time it issues a write instead of a read, so it pulls this line low, or the data line low, in this bit cell, and then it waits for the acknowledge on the 9th clock, and then it sends out a byte, which is the address from which it wants to read, and the slave is expecting that byte to be that address. And then what's next, if the master keeps clocking, it will clock out another byte of data, and that byte gets written to the address that was pointed to by this byte here. If the master continues to clock out data, it will the slave will receive that data and put it into subsequent addresses. Each time it writes to it, that address increments as well. So when the master is writing out data, it waits for the acknowledge. There's the 9th bit, or the 9th clock, and the slave will acknowledge by pulling the line low. And it will keep doing this until the slave stops. And the slave just stops clocking, issues a stop condition, and that's the end of the transfer. Now, if I want to read, I could read from this address. If I just did this with 3 bytes, slave address, the address it wants to read from, and then the data that it writes to that address, if I'd switched it over and did another read like this, that first byte read would be this one here that was written previously. But now I want to write or read from a specific address, and this is how it gets done. So again, the master issues a start, followed by the slave address, followed by a write again, waits for the acknowledge, then it clocks out the address that it wants to read from, waits for the acknowledge, and then it issues another start condition. And this is also called a repeated start. And again, it follows it by a slave address. This again, it's in this case it's a read instead of a write, so the 8th bit will be high. It waits for the acknowledge from the slave, and then it starts reading the data in 1 byte at a time for as long as it keeps clocking. And remember, I said that the address pointer in the slave increments each time. So I can read a whole bunch of data from the device all in one go with this one stream here. When the master is finished reading, it sends a not acknowledge. Remember, the master is receiving data here and here, so it acknowledges by sending an acknowledge each time it reads the byte except for the last byte, and then it'll send a not acknowledge by letting that line, the data line, go high, and then a stop pulse. So that was a very quick description of how the I2C bus communicates, or how devices communicate on the I2C bus. It's not very complicated, although I've read people in commenting in blogs at how complex the I2C bus is, but I find it quite simple. And you only really need two separate functions that you can use, a read function and a write function, and that will do everything you need to do in communicating on the I2C bus. Now here's a circuit set up as a quick demo. There's a bit more stuff on here than what's needed for the demo, but I'm working on another project. First off, buried under the scope probes here, that's an ATMEGA 328. This is my version of an Arduino, and I've got the scope probe hooked up to the SDA and SCL lines, these two here, to show you what the signals actually look like in real life. Over here is a little Nokia, was it 5115? I can't remember the number exactly. Display, liquid crystal display. It runs on an SPI bus, and perhaps I'll do a video on that bus later and maybe use this as an example of how it communicates on that bus. Over here is a micro SD card slot, card holder, and it also communicates on the SPI bus. But over here is the accelerometer. You can buy these little boards anywhere pretty much. On eBay or various other distributors have them for sale as well. They're really cheap, a few bucks each. Let's zoom in on it here. The accelerometer is the chip in the middle there. Even on the silk screen it shows the different axes. The y-axis is this way, the x-axis is that way, and the z-axis is vertically. So that's very simple setup. You can see there's only 4 connections to it here. Oops. Power and ground, and the I2C, 2 lines for the I2C bus. Power in this case is 5 volts, even though this is a 3.3 volt device, but there's on there you can see this tiny little 3-pin device. That's a 3-terminal regulator, and it drops the 5 volts down to 3.3 volts, which is what this actually operates on. The pull-up resistors are on the board here, and they're tied to the 3.3 volt bus. And over here on my ATMEGA, I have no pull-ups. I just use the pull-ups on the board itself, on the accelerometer board itself. And even though it only goes as high as 3.3 volts, the ATMEGA can still see that as a 1. And then when the accelerometer pulls the data line to the ground, it looks like a 0, of course, to the ATMEGA. So in this case, you can interface it directly. Be very careful, though, not to have any pull-up resistors on your board if you're using something that's other than Arduino, because you don't want to be pulling these lines to 5 volts. You could damage this chip driving the SCL and SDA lines with 5 volts. So here's a captured image of I've got the microcontroller just in a loop that's constantly writing 1 byte of data to one register in the I2C device, in the accelerometer. So you can actually look at what's going on here. Here are the clock pulses along the top here. So there's 1, 2, 3, 4, 5. Where we go? Let's get this right here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 8 for the data byte, and then the 9th one for the acknowledged bit. So it clocks out the data most significant bit first. So we've got a 0. Let me see here. Am I getting this, reading this right? Because I think the address we're supposed to see is a 5.3, which is what it looks like on the screen there. So you got a 5. Yes, if we look at just the 7 bits here, and then if you consider the 8th bit out here of a word is 0 here, so that's 101, which is a 5. 4 and 1 is 5. And then a 0011, which is the 3. And then here is the 9th one. So the slave address is from here to there. So this is the lowest order bit. This is bit 0, 1, 2, 3, 4, 5, 6, 7, 8. So 8 isn't here. So that's how we get the 5.3 out of this. The next bit is a 0, which is because we're going to write the address that we want to write to in the next byte. So we've told the slave that it's a write, and then this next bit after that, after the 9th clock, is the acknowledge from the slave. So the slave is actually there. If I were to unplug the slave, you wouldn't see this. This would actually go high, and my software is written that the master will keep trying 20 times, sending out this information here until it gives up. And then a second later it's going to try again, because I've got this happening in a 1 second long loop. But for now, because the slave is there, the master detects the slave, and it goes on. And now it wants to output the byte that it's, or the address that it wants to write to, which is 001011. That's that right? 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So it's 00102. Looks like 2C is the address it's writing to. The 9th bit here, or the 9th clock here, is low, so it means the slave is still there. It's acknowledged that. So this is the address it's going to write to. And if I slide this over and we look at the last one, and then this is the data byte that it's writing, the master is writing to the slave. Again, the 9th clock bit here is the acknowledge. Now let's go back to the beginning, because I forgot one important signal. So if you look here, we've got the clock line high, and then the master, or the data line, goes low while the clock is still high. So this is our start condition right in here, this very narrow bit here. It doesn't take much to do it. And then if we move it over to the other end and we do the same thing, we see that the data line is held low while the clock is allowed to go high, and that's the stop condition. Alright, here is the demo hardware actually working now. Just see what the data is on the screen there. Oops, there we go. So I've got the acceleration data from the 3 axes, and if I tilt it, you can see the y-axis changing this way. If I tilt it up this way, you can see the z-axis changing, and also the x-axis and the z-axis changing. But anyways, that's the raw data coming out of the accelerometer, and it's affected by gravity. So the z-axis, which is operating in the vertical direction right now, it's reading the force of gravity, the 236 there. I'm just slightly tilting the accelerometer on the board. It's not perfect. It's not a calibrated device, so even though X and Y are not being affected by gravity, they still show a bit of an error there, but that's not too bad. If I were to turn it completely upside down, the Z-axis would read negative about the same number. So if you can see the X-axis changing. It goes negative this way, and it goes positive that way. And then the Y-axis goes negative this way, and it goes positive. There, you can just see it going the other way. So that's the accelerometer working. Now let's have a look at the TWI peripheral inside the ATMEGA microcontroller. The heart of it is a shift register here, which is where the parallel data is written in bytes, and then it gets shifted out on the data clock, or the data line here. There's only a couple of registers that you really have to be concerned about. These four: the baud rate register, the data register, status register, and the control register. The address register here isn't needed when you're just being the master, and that's all I'm going to talk about here is the ATMEGA as being the master. So the two lines are here, clock line and data line. The bitrate register is written to determine the speed of the clock line, and there's a calculation I'll show you in a moment how to figure out what value you put in here for what clock rate that you want. The control register here controls what happens in the bus interface unit. It makes the bus interface unit produce the start and the stop conditions, as well as shifting out the data and shifting in the data. The status register is it just holds a value that indicates what just happened. So whatever this peripheral was doing, and when it's finished, a value gets written into this register, and you can look at that register and determine what was going on, if everything worked properly or if there was an error. So if you scroll down and look at, oh, here's the calculation for the baud rate register frequency. So this is the clock frequency that you want to, the I2C clock frequency that you want to use, and then you can rearrange this formula here to get the baud rate register value. Actually, just no, you don't. It's I was going to say substitute these two for each other, but it doesn't work that way. But anyways, you can reorganize this formula here to get this value out, so you can calculate what it should be. There's a prescaler. The clock for the I2C bus is derived from the main oscillator, the 20 megahertz oscillator or the 16 megahertz oscillator, whatever your microcontroller is being powered by. And there's a prescaler that divides that main oscillator by 1, 2, 4, or 16, I believe. And in my case here, I just leave it at 1. I don't need to clock it down that much, because I want it to run the SCL frequency to be the maximum. And the other registers that you want to work with, there's a whole bunch of stuff here. A quicker way to do that is to go down here, register description. Here we go. So this is the bitrate register. It's just 8 bits. You write a value into it that determines the clock speed. The control register is how you actually get the thing to do something. This int bit here is set when the peripheral has finished doing what it's doing, and it generates an interrupt if you've set this bit here, which is the interrupt enable, and then it will generate an interrupt. Then the processor will go off into an interrupt service routine that you have to write. But the example of software that I'm going to give you here does not use interrupts. But in order to get the peripheral to actually do something, you have to clear the interrupt, and once you've cleared it, then it will do whatever you've asked it to do, and then when it's finished doing that, it will set this bit again. And so most of the time this bit is actually set. When the peripheral is idle, the bit is set. This bit here is to enable the acknowledge. So if you're receiving bytes from the bus, you want to, the master puts out an acknowledge or a not acknowledge. If this bit is set, then the master will put out an acknowledge, and if this bit is clear, it will be a not acknowledge. If this bit is set and then this one is cleared, the peripheral will produce a start condition on the bus. And similarly, if this bit is written to 1, set to 1, and the interrupt flag is cleared, then the peripheral will output a stop condition on the bus. This bit gets set if there was a collision on the bus, more than one device tried to write to it at the same time. This bit will be set. And this bit here, when set, it just turns the peripheral on. When it's cleared, the peripheral is turned off. Let's go down to the last one here, the status register. So the upper 4 bits of the status register, or the upper 5 bits of the status register, is the actual value of the status. And in my software, I do use the status register a little bit. I do read the values and look at them and determine what to do based on these values. If you're going to write an interrupt-driven I2C interface, you need to read this register all the time, because you have to determine what's going on. But in my case, I wrote a very simple routine, or very simple driver, I2C driver, and I don't really need to use this very much. These 2 bits are the prescaler bits, and you just set them to determine what prescale value you want. I was actually incorrect. It's 148 or 1416 or 64. Let's look at the software here. This is the I2C library that I've written, and it's a pretty simple library. It's not interrupt driven, it's blocking, so every function here will block until the peripheral, the TWI, has finished what it's doing. I got some of these ideas for some of the routines in here I got from the WinAVR compiler. It came with a few examples of how to use the TWI. So you need to include the TWI.h library, which mainly just names all the different registers and the bits in the registers that you're going to be using. Defines.h is my file, and it just is a catch-all for different defines that are going to be the same for every file that I compile, and particularly it's the frequency of the main crystal that runs the microcontroller, called FCPU. I do an error count in the code here. If there's something goes wrong when I'm trying to write something to the data bus or whatever, I count the number of times that I retry, so that it doesn't hang forever. And once it exceeds 20 retries, then the function will return with an error code. And this is just the maximum value of retries that I'm going to allow. This value here is the frequency of the I2C bus. This is 400 kilohertz, 400,000 here. Most devices that you buy today will communicate quite happily at 400 kilohertz, which isn't particularly fast. SPI can go to multiples of megahertz, but that's one of the disadvantages of I2C, is the slower bit rate. But the initial standard was 100 kilohertz, and it was up to 400 kilohertz. There's new standards out there now that go up as high as 5 megahertz, but they're not compatible with this version here. First of all, you have to initialize the peripheral and get it ready to go. And the first thing you need to do is make the 2 pins that hold the SDA and SCL lines as inputs. And it's pins 5 and 4 on port C. And if you write zeros to those bits that represent those pins, it'll make them an input. I need to disable the internal pull-ups. There's pull-up resistors on I think all of the I/O pins on the microcontroller, and I don't want them to be connected to the 5-volt supply, because my peripheral in this case is a 3.3 volt device, and I don't want to be tying the pull-ups to 5 volts, or it could damage the chip that I'm talking to. So here I just, in order to disable the pull-ups, you write to the port C register. The port C register is actually the register that you read to get the digital value of the register of the port. But if you write to it, it controls the internal pull-ups. And wherever there's a 0 here, it turns off the pull-ups for that particular pin. TWSR is a status register, and the peripheral will return a value that represents the status, which is the results of the last operation. and it can be used to detect what the peripheral was actually doing. If you're running this as an interrupt driven system, you need to have some way of telling the interrupt routine where you were, or the status register also show you if some errors occurred. And I do read the status register and look at it at the values in a couple of places in the software here. In this case, I'm just clearing it to make sure it actually is 0. On power up, it will be. But if the microcontroller is issued a reset, I wanted to make sure that the status register is still cleared, even though it may actually be cleared on reset. I can't remember exactly how it works. Here I am setting up the baud rate register. This determines how fast the clock is, and I showed you the formula that you have to use to compute the value of the baud rate register depending on the frequency of the I2C bus. And so this is the macro that I declared up, or the constant that I declared up here earlier, which is 400,000. FCPU is declared in my defines.h file, and this is the calculation to figure out the value that goes into the baud rate register. What this does here is if the FCPU is below 1.6 megahertz, it just sets the baud rate register to 0, which means the fastest clock frequency you can have at that, or the fastest I2C frequency you can have at the whatever clock frequency, FCPU frequency you have. And then I turn on the peripheral by setting this bit here in the control register, TW enable. So this is how you issue a start. You simply write to a bit in the control register, which is right here. SDA is the start bit in the control register. Now, I talked about the interrupt bit before. The interrupt bit is normally high, which indicates it would generate an interrupt. Whenever the peripheral, the TWI peripheral is idle, int is high. In order to get it to the peripheral to do something, you have to clear that int bit, and that bit will stay low as long as the peripheral is doing something, and when it's completed whatever it's doing, it sets the int bit again in order to generate an interrupt. So here I am clearing it, and then that starts the peripheral up, and I automatically just set the enable bit every time I affect this control register, just to make sure that the peripheral is actually turned on. So while the TWI is issuing a start condition on the bus, it takes some time to do that, which is more time than what the CPU can do. The CPU is very quick, or the microcontroller is very fast. So what I do here is I wait for the TW int bit to be set, and so it just waits in this while loop while TW int is 0. When it becomes 1, it falls out of the while loop here, and then I go into the switch statement. And this is one of the times when I look at the status, the TW status, and if the status indicates that a start was issued or a repeat start was issued, then everything's good, and I return a 0. So what we're looking for in this function here is a return of a 0, indicating that there was no errors. If status was anything else, I just return a 1. I don't really care what the value of the status was. I just need to know that there was an error, and the routine that calls start can actually do something about the error and maybe try to issue another start again. The stop condition is issued in the same way, except you set the STO bit instead. And there's no status that's associated with the stop condition, so I don't bother to check it. But here's the wait loop. And it's actually testing the stop bit. I'll have to look it up in the data sheet to see if it should be actually the int bit. I can't remember. This does work. I've run these routines have been working just fine for the last couple of years, so obviously this is correct, but I'm going to have to double check that. But again, like I said earlier, there's no status associated with the stop, so don't bother checking it, and there's no error condition here. Basically, the stop condition, it gets forced onto the bus regardless of whether the bus can take it or not. If I want to write a character to the data bus, this routine is called I2C putChar, and it returns a value as well, and it returns an error code, because if something goes wrong while the character is being written to the bus, the TWI can detect that, and I can test for that and return an error code if something went wrong. In order to write a character to the bus, I put it into the data register, and then I clear the int flag again to start the peripheral, and then I wait for the int flag to be set. While the peripheral is doing its thing, sending out the character, the microcontroller is going to be sitting in this really tight wait loop, while loop, until TWINT goes high. And here I check the status, TW status, and if any of these statuses are returned, which is a good thing, the byte was received and acknowledged by the peripheral, or by the slave device, so I return 0. If I get any of these values, like there was a NAC, as if what it means is that there was no slave device there, or it wasn't able to receive the byte, then there's an error. And so if any of these error codes come up, I return a 1. And if I've missed anything, I just put a default here and return a 2. But any non-zero number returned by this routine here indicates there was an error, and the calling routine can actually do something about the error, perhaps resend the byte or do something. I'm not sure what, depends what's going on. To receive a character from the bus, this routine gets called, and it returns the character that it receives from the bus. So all you have to do here is set or clear this EA bit, which is enable ACK, or acknowledge. And if you set that, it means that the TWI will issue an acknowledge after the character has been received. And it will, and you start the peripheral the same way. You just clear the interrupt bit, and then you sit in this loop waiting for the int bit to get set again, meaning that the character has been received. Now, if there's a problem on the bus for some reason, no character gets received, this routine will block forever. It will sit here and forever and ever, and your microcontroller will hang here. I should probably put something in here to do a count or something like that, sort of time, the time it takes to be in this routine, and if it exceeds a certain amount of time, then it should return with an error code or some indication that there was an error here. This is not good practice to write your code this way. You don't want any routine to ever hang the processor for any reason, at least forever. But assuming that everything is okay on the bus and the character gets received just fine, the interrupt bit will be set, the while will fail, and you simply return the value in the data register. If I want to receive a character and send a not acknowledge instead, which I would do on the last byte of a stream of bytes that I was receiving, it's the same as the previous routine, except there's no setting of the acknowledge enable bit. But it does the same thing. Again, it would block here until it receives a character, or if there was no character to receive, it will hang forever. Something I'm going to have to look at in these two routines here and try to figure out a way to make them a little more robust so they won't hang the processor. Now you can combine these 4 simple functions together to create 2 functions called I2C write and I2C read, and they basically duplicate the two of the streams that I showed you in my pencil sketch to read and write data to the I2C device. So let's start with the read first, because that was the one that I showed you first. I2C read is called with these 4 parameters. The first parameter is the slave address of the device that you're going to write to, and it's the not shifted to the left value. You just write it. When you look at the data sheet, they will give you the slave address in 7 bits, and this is the value that you actually use, and you write this in that first parameter. Length is the number of bytes to be read, Address is the address inside the device, the slave device that you want to start reading from. And this is a pointer to a buffer or an area of RAM that you've put aside to store the data bytes that you receive. And you must make sure that that buffer is big enough to hold all the bytes that you want to receive. This routine is capable of receiving up to 255 bytes in one go. So make sure your buffer is big enough to do that. Obviously, you probably won't want to make it that long, but in some cases I do it where it's 22 bytes long, and it works just fine regardless of the number of bytes you put in here. Now I'm going to do an actual error counting here, so I set up this variable here, restarts, and I give it a maximum of this constant, which we declared as 20 earlier. First thing I check is if length is 0, it means there's nothing to do, so I just return. Now here I put a label here, and this is not the best C programming, but it's the easiest way to implement this. I put a label in here because what I'm going to do is I'm going to issue the I2C or I2C start, and if it returns an error, then it goes down into here and it will execute this code. If I2C start was successful and the start condition was put on the bus without any problems, then this code here is not going to execute. So what happens if there is an error? It's going to decrement restarts and check to see if it's equal to 0. And if it restarts does reach 0, then I simply return 1 here, indicating that my I2C read failed. And because you're looking for a 0 here when you return, when this I2C read returns, you want it to return with a 0, which indicates that it was successful. So returning a 1 indicates that the I2C start didn't work. And what happens here is if restarts is not equal to 0, then it does a goto. And this, like I said, is not the greatest C programming method here. Goto statements shouldn't really be used in C code, but this was the easiest way to implement this. And it simply will go back to here again and just repeat this whole whole if statement again. And it'll keep looping through here. Every time there's an error, it will loop through here until restarts equals 0, and then it returns. So this way it never hangs for very long, and it'll issue 20 starts if it has problem issuing a start condition on the bus. So the next thing is, after it's written the start, it's going to write the control byte, which is the slave address plus the read-write bit. So here we build the character that we're going to output, and that includes the slave address shifted left by 1 bit, ORed with TW-write. And TW-write is defined in this case as 0, and this is defined in the TWI .h file. And so you don't have to worry about what this actually is. It just says we're going to write the value of this character on to the I2C bus. And the same thing occurs here. If there's an error in this I2C put car, this loop here counts them. And if they exceeds the number of restarts, then I issue an I2C stop, and then I return with 2. Again, I'll go back to here. The same label occurs here. So if there's an error and it hasn't decremented restarts to 0 yet, it just hits the goto here, goes back to the beginning, issues another start condition, plus putting this slave address out again. And so it can run through this loop 20 times. If there's no slave on the bus, that's what happens here, is that it issues the start plus this slave address with the write byte or the write bit set. And it'll just keep doing this as many as there are restarts, which would be in this case 20 times. And then it'll return a 2 if there was an error there. But assuming that the slave address was accepted on the bus, the slave was there and it returned an acknowledge, everything's good, we're going to write the address that we want to read from. And we put that onto the bus. Now I could do another error checking here, but I decided if it got through all of this successfully, then everything's happy on the bus and I shouldn't have any more problems. And so actually that's not true. I don't count it. If there I do check the error, but if I don't do a restart, I just simply return. Probably what I should do here is put a stop on the bus and then return. Some more changes to the code here. This hasn't been fully played with. But anyways, so what we've done here is we've issued the start. We've written the slave address with the read-write bit set to write. We've now output the address that we want to write to or read from, and then we apply the repeated start again, or we apply another start on the bus, a repeated start. This time we output the slave address, but this time with the read-write bit set to read, because now we're telling the slave device that we want to read. Now here we are in this loop, and we're receiving our data bytes. This is I2C get car, and we just put it into buffer and increment the buffer pointer each time through this loop, and it goes through the number of data bytes, the number of bytes that we want to receive. It goes through that loop that many times until length is equal to 1, not 0 in this case. So from if there was, I wanted to read 6 bytes, this will go 6, 5, 4, 3, 2, and then it stops at 1. And then it issues this is the get car with the acknowledge being issued, and then the last byte, which is this one here, it issues the knack. Finally, we're done on receiving the data, and we issue an I2C stop, and then return 0, indicating that this function returned or performed correctly without error. So that was the I2C read. Now let's look at the I2C write. It's pretty similar to the read. These are the steps. Apply a start condition, put the slave address with bit 0 equal to 0, which means a write, onto the bus, and then put the byte address that you want to write to, like the byte address in the slave device that you want to write to, onto the bus, and then start writing the data bytes out to the bus. And just keep repeating this one until all the bytes have been written, and then apply a stop condition. So it looks very similar, as I said, to I2C write. We have to give it the slave address of the device that we want to write to. We have to give it the number of bytes that we want to read, and we want to give it the address that we want to read from, and then we have a buffer from which we're going to take the data bytes from. And again, I'm going to count errors here. So restarts is set to max restart, which in this case is 20. If length, just do this check again. If length is equal to 0 or less than or equal to 0, just return, we're done. We don't have to do anything more. So I've written another label here, write restart. Again, not good programming practices because I'm using a goto here, but like I said, it was the easiest way to implement this. So again, I just issue the I2C start, and I check for errors. And it'll loop here, counting errors until it finally fails. If there are no errors, nothing will happen here, and it will just fall through. None of this code will get executed. Start condition's been issued. Now we're going to write out the slave address with the write bit set. And again, like previously explained, this just simply counts errors if there are any. And if there's no errors, it'll just drop straight through and continue on. And then it writes out the address that you want to read or write to. And then finally, in this loop here, it writes out all of the different, all of the bytes that you want to write in a sequence. Using the put car routine, and it just simply increments the buffer pointer each time through the loop. If there's any errors here, I2C put car, it just returns an error code of 4. So again, we're looking for this routine I2C write to return a 0, meaning that it was successful. If it's non-zero, it means it was not successful. So that is a quick rundown of how you write code to make the I2C bus work. So let's have a quick look at the ADXL345 library here that I've written in order to operate the accelerometer. And you have to include the I2C library here, and actually it also includes its own library. It doesn't really need to, I don't think, but I do that. Anyways, here's the slave address that I was reading off the oscilloscope of 5.3. Remember, as I said, it's not the left shifted one, it's simply the right shifted, and then the I2C routine does the left shifting for you to put it into the upper 7 bits of the slave address, or it's called the control byte. And these are all the different registers that it has. I'm not going to go through any detail on those. I'm just going to show you how I write to a particular register. So this is a function, set power control, and so it takes a data byte and it writes it to the I2C bus. So it calls I2C write. Here is the slave address, which you can see up here has been defined as 5.3. I'm going to write just 1 byte. This is the address within the device that I want to write to, which is 2D. And then here is the data buffer, or actually here's the, well, since it's only 1 byte, you can just give the address of the data and it'll write out the 1 byte. Now, I showed you earlier that this routine will return an error code. I could use it to check if there was an error code and do something about it, but I've made these routines pretty simple, and I haven't bothered to do that. Now, to read the accelerometer data from it, let's just scroll down. There's a few routines here just for setting up the accelerometer to make it work properly. Here we go. So what the manufacturers of the accelerometer have done is put the 3-axis, the data for the 3 axes in a sequential order in contiguous bytes, and it takes 2 bytes for each of the axes, X, Y, and Z axes, and because it's 16-bit data that is returned for each axis for the acceleration data. And so they've ordered them in order of X, Y, and Z. So if I just read 6 bytes starting with the X register, I will get all the values of all of the 3 axes. And this is what I do here with this function called ADXL345 get Excel data. And I simply pass the address of the buffer that I want to put the data into, and I call I2C read. And again, here's the slave address that you're going to write to of the device, the slave address of the device you're writing to. This time I'm going to read 6 bytes, and I'm going to start at the address ADXL Excel data, which is address hex 32, and then here's the address of the buffer that I'm going to put the data in. So that's how you use the I2C routines in order to communicate with the accelerometer. That's about it for a quick look at the I2C data bus. I hope you guys understood how this works. It's not as complicated as I think some people make it out to be. I find it really easy to use, especially when I've written these routines and debugged them and got them to work. It's fairly simple to set them up for any device that uses the I2C bus. So, if hopefully you guys got something out of this and appreciated the information here. If you enjoyed it, give me some comments. Let me know some other things that we could talk about or that I could do a video on, and hopefully pass on some more information to you. If you enjoyed this video, give the YouTube video a thumbs up. So, thanks for watching, and I'll catch you the next time. Bye for now.